Okay. Time to begin. Wait, there's no classes today? Huh. Oh my god. This chat, man. Let's play some music. Alright. Okay. Alright, yeah. Okay. Let's congratulate algebraically challenged here. Good job. Alright. Okay. Alright, so today class, meaning all of this week really, we're gonna pay special attention to this concept of normal subgroup, quotient groups, that's what this week will focus on. And this topic, this area of normal subgroups and quotient groups is probably the most subtle so far. So students, don't slip at this point. Stay on high alert and read chapter 9. This is all in chapter 9. And watch the videos carefully and ask me questions. In office hours in Discord, ask questions on Discord to each other. Okay. So, the first thing I want to talk about today. So the main thing the thing I really want to talk about today is point number 2. What kinds of tricks become available in the presence of a normal subgroup? Okay, in the presence of a normal subgroup, what kinds of tricks become available? I've noticed that in the Discord, people have been wondering, hey, maybe once we learn about normal subgroups, BMP said that maybe you can use some fancier trick that helps you do the case checking or something. Someone asks you to classify all groups of order 8. Yeah. When we have a normal subgroup, certain tricks open up, and I want to talk about that. But the first thing I want to talk about is more theoretical type thing. This is theory. This is actually this is more practical, the number 2. And then if I have time, I'll summarize all the tricks that we know so far in just group theory. But probably I won't have time. Okay, so normal subgroups equal kernels. So let's talk about that. Normal subgroups are precisely kernels. This sounds weird. Why did we have so many strange definitions for normal subgroups if at the end of the day they're just kernels? Well, it's one of these situations where you choose what starting point definition you'd like, and then the fact that it happens to be the other, have another description, is some surprise. It's one or the other, folks. So it's good to have both at the same time in your mind, both of these concepts, because some points of view are more relevant in certain situations than other points of view. So let's talk about this. Okay. So on the one hand, we have the set of all normal subgroups of a group. And on the other hand, you can imagine the following set. All kernels of all conceivable homomorphisms. So imagine all the ways that you've been able to figure out how to map G to some other group. And label all the kernels of those things. Yeah, well, these two sets are the same set. And that's what I want to go through right now. These two sets are the same set. Okay? This is just another way of thinking about what normality means. It means your group is actually a kernel of some map. All right. So let me go through this equivalence. It'll always feel a little bit empty. Okay? So let's do that. Okay, so let's go through this. One way. Suppose you have a kernel of some homomorphism. Then the kernel is a normal subgroup. All right, it's one of these special types of subgroups. In other words, the kernel is stable under conjugation by G. For any G and G, for anything in the kernel, the conjugation remains in the kernel. That's the statement. All right, let's check that. Let's check it. Indeed. Let's check what this output is. If we're trying to say that the element GK G inverse is in the kernel, maybe we should map it under phi. That sounds like a good idea. So this is by homomorphism. All right, so that's the same thing as that. And this is this, because K is in the kernel. All right, great. Great. So kernels are normal. Kernels of homomorphisms are normal subgroups. Great. So in other words, these two sets, there's an inclusion one way. There's an inclusion we just established one way. Why is this not working? Alright, we just established that way. Now we gotta establish the other way. Other way. Suppose H is normal. Okay, that's our little symbol. Then, consider the quotient homomorphism. Only available to us because H is normal. Can't even talk about this homomorphism. You can always talk about the function of sets, but you cannot call it a homomorphism. Hello, Pruds. I don't know who you're referring to. Probably Kappa. Okay. So, consider the quotient homomorphism. Its kernel is the set of elements such that AH is H. Remember that the identity element in the quotient group is the coset H itself. So what I just wrote out is the map here is, let me write that out. An element goes to its coset. So if I'm asking for the kernel of this map, I want to know which elements produce left cosets, which are the trivial coset. But that's exactly the set of elements in G such that A is in H to begin with. i.e., the kernel of the quotient map is the subgroup that you were looking at in the first place. Okay, that makes some kind of sense spiritually. And so there you go. H is a kernel. So H is a kernel of some kind of map out of the group. And you've got your other inclusion. All right, so these two are the same set. Is quotient homomorphism the only homomorphism that works in this proof? In a sense, Sloth, yes. In a sense, that is exactly right. Why overcomplicate? Wait, what's the overcomplication? I don't understand. Wait, what's the easier way? Well, I mean, well, I don't know. It's yeah. I mean, it's a good question. You could try to come up with other ways of doing this. In fact, the question has important content. There's actually something to the statement. Was our hands tied? Are our hands tied in this proof? That the content of the answer to that question is called the first isomorphism theorem or something like that. There's actually a very important idea behind answering that question thoroughly. It's one of the 3 isomorphism theorems whose content is definitely adjacent to that question or answers that question in a way. Yeah. Yeah, definitely. Well, yeah. One shouldn't just put the pen down when something's easy and it's done. The point of math is not to just have the answers. It's to understand the relationships and possibilities. Relationships between ideas, and the best way to do that is to ask, was there other ways to do this? I think that's actually more in the spirit of a mathematician than to just write an answer and put the pen down. Great. So awesome. Also, by investigating other approaches to a problem, you better understand what are some common mistakes or bad paths that one should not go down, whereas someone who simply puts the pen down after reading the first obvious proof, they won't have that kind of they won't know the complement of the set of facts in a textbook, but someone who does adventure out knows what the complement looks like. So it's kind of important to try to prove things in different ways. Okay. Next. So kernels, so when someone asks you, hey, find normal subgroups. Find normal subgroups. Well, in the beginning, if you didn't know this wormhole, oh, they're just kernels. Then you would try to use the initial definition and say, oh, well, I gotta delicately choose some particular elements so that when I conjugate, it just keeps this within itself. Or, oh, I have to choose a subgroup where the left cosets are the same as the right cosets. It seems like a real puzzle. But this wormhole allows you to just change to the problem of, hey, write down every homomorphism, as many as I know, from my group to another group. All right, so from here, you get a bunch of examples that maybe didn't occur to you initially, but immediately flow from here. So you get tons of examples. For example, you just get immediately, like, I mean, you would have gotten these eventually, but you know, it's better explained by this wormhole, like SLN. They're determinant 1 matrices. It's a normal subgroup. Because there's a map called determinant that takes the matrix, outputs a determinant. Kernel of that map is SLN. All right, so every time you come up with a map from the group to somewhere else, look at its kernel, you'll get a bunch of examples. Okay, there's another one. We saw once that there's a surjective homomorphism. There's a curious surjective homomorphism from S4 onto S3. This is in office hours somewhere. And there's this curious map. If you look at the kernel of that map, it's this subgroup. This is and this subgroup, we had a name for it. It's called the Klein 4 group. It's isomorphic to the symmetries of a rectangle. Flips and rotations of a rectangle that's not a square. All right, so this symbol means surjection. So there's a normal subgroup for you. Okay, go through as many examples that you know. For example, here's another one: the sign homomorphism. Even or odd? Even means +1, odd means -1. The sign homomorphism, the kernel is AN is a normal subgroup of SN. Okay, so etc. On and on. So how to think about this? How should you how could you digest this? The normal subgroups measure in how many ways can the current group G get sort of contracted to some other group. But here's a way to think about normality. At least the presence of normal subgroups. In how many ways can our group map non-injectively because injective maps have trivial kernels, so that's not measuring anything. That's a trivial subgroup. But if you're interested in sort of non-trivial normal subgroups, the set of non-trivial normal subgroups, in some sense, measure how many non-injective maps there are from the group to another group. Non-injective maps think of as compressing, squashing. You can think of this as squashing the group to a smaller group. And so the presence of normal subgroups you can take, or the lack thereof, the lack of normal subgroups, you can take to be a measure of incompressibility of the group. The group is allergic to being squashed down to a smaller group. Squashed. That's to be thought of as opposite to finding a smaller subgroup of G. That's always easy. Just take your favorite element and take the cyclic subgroup. It's easy to produce subgroups of G. It's much harder to squash a group to a smaller group, to cancel out a subgroup, to mod out by a subgroup, to quotient out by something. It's much harder to do that. And so in your mind, you should think of this discussion of existence or non-existence of normal subgroups as a measure of compressibility or collapsibility of the group to a smaller group versus not. Okay, great. So more on that later. We will investigate which groups are collapsible like this and which ones aren't. We'll give names to that dichotomy at least. Okay, great. So now let me move on. Let me talk about what happens in practice when you're doing homework problems when you have a normal subgroup in your hands. What can you do? What can you do when you have? This was the second thing I wanted to talk about. And it's, I don't know, when I first learned this group theory subject, I kind of had to like figure out these tricks only in retrospect, and I wish someone had just like, boom, like come out straight up say the thing so that I didn't have to guess whether I was using it right the whole time. So here's what can happen when you have a normal subgroup. So trick number one. So again, our context is that H is a normal subgroup. Okay, if you have any other subgroup, then the set, remember the set from the HK trick? Think of this as a HK trick version 2 in the presence of normal subgroup. Then the set HK, just a set of products, H's times K's. The set H times K's, that's again a subgroup. Here's why. Look, if you multiply one of these products with another one, then remember one way of interpreting normality is that, like, if you know that we know this, for example. We know that conjugation takes H and outputs something else in H. So you can commute across elements of H at the expense of changing that element. So this will be the same as you can sort of swap out in the algebra. When you're doing algebra, you can swap the order, but the H gets transformed to an H prime, some other thing. You have to allow that freedom. But this is, again, an H times a K. So this is the basic reason why, you have a subgroup. You should check inversion too. It works the same way. Inversion, you can move things across and get closed under inverses. Well, so this is good, and we know the size of this set. It's not just any old. We know more. Just remember, I just want to remind you, the size of this subgroup. Now I can use the order symbol. Is this formula. And you've already seen ways in which this is useful. But now we can actually guarantee that this thing is a subgroup. And so, you know, Lagrange's theorem comes in and so on. Okay. So trick number 2. Trick number 2 is more of an observation. Okay, but you can use it. All right. So if K is any subgroup, then conjugation. By elements of K produces a homomorphism from K to automorphisms of the group H. Now this is the group of automorphisms. Not just random permutations. Each element in here is an isomorphism of H with itself. A group isomorphism. You get this. You get a conjugation homomorphism. Not a random function. What is this map? An element K goes to conjugate by K, which I'll just write as K insert element K inverse. This is a group homomorphism, is an automorphism of H. Sometimes you write a little arrow that goes to the same set. Okay? So this is a homomorphism between the group K and the automorphisms of H. The fact that you can even write this arrow requires that you have a normal subgroup, because a normal subgroup is such a group that's maintained, preserved under conjugation action of the whole group. In particular, it stays within itself under conjugation by a subgroup, namely K, whichever K that came up in your case checking proof. All right? So how do you use this? How do you use it? This is an obvious observation in a sense, but how do you use it? Usually, typically, the main use comes from the following. You understand K very well? Like a cyclic group of order prime. Oh, that's quite a simple, that's a simple group. Yeah. Understand K well? You understand the automorphism group of H really well. Okay, for example, you know how big it is. Maybe you know the order of that target group. Okay, that's good information. Ideally, you'd want to know the entire structure of any group that shows up. However, sometimes just knowing the order gets you far enough thanks to Lagrange's theorem. So understand K, understand this thing, and then with both of these understandings, maybe the set of homomorphisms from K to H, maybe there are very few. Homomorphisms, even just abstractly. From K to out. That will tell you a lot, because it'll tell you how these kinds of multiplications, it'll tell you answers to these types of multiplication problems in the group. Okay? Now I want to show you a third trick. It'll be used, it's useful in conjunction with trick number 2. Third trick. This is not so much a trick that relies on the existence of a normal subgroup or having a normal subgroup in your hand. It's just a trick. All right? It's another HK trick. Okay. Pruts? No. It won't even be Pruts. Matrices with given eigenvalues is not a subgroup at all, because you got to have the identity matrix. Okay. Oh, Kappa. Here's one way that you can use trick number 2. Ready? Okay. So let's just look at. I'm gonna produce just a trick. It's just a trick number 3. Suppose H. Don't assume anything about normality. Suppose H and K are 2 subgroups of a group G, such that 2 things. They intersect very little as possible. Okay? And 2. The 2 groups commute with each other. But let me say what I mean by that. H times K equals K times H for any element in the first group and for any element in the second group. Suppose you got 2 groups that you somehow know commute. All right? Then this product set happens to be equal, this is obvious, to the other way product set, and this is a subgroup of G which is isomorphic to the product group H cross K, the group of pairs. If you have 2 groups, you get a third one by putting a comma between elements and computing in parallel. Okay? All right. So now, you can. I'm gonna. The proof of this is very easy, but I want to show you how you use trick number 3 with trick number 2. Suppose in trick number 2, you found that like K and automorphism of H were incompatible in the sense that there's only the trivial homomorphism from K to automorphisms of H. Suppose you therefore deduce that KH times K inverse equals H for any H in here. In other words, conjugation always is the identity homomorphism. Well, that is just another way of saying that H and K commute. And therefore, H times K is a potentially very large chunk of the group that you have pinned down. You have figured out a huge chunk of your group G. Maybe even all of it, if you arrange things, if the stars align. Maybe you've proved then that the whole of G is H cross K, and maybe H is Z mod 5Z and K is Z mod 7Z. I don't know. And maybe that helps you prove that every group of order 35 is abelian. Maybe. I don't know. But this is how normality can be exploited. It's the most common way that you exploit normality. You use this conjugation homomorphism, and hopefully there's not many options, and then this thing swoops in. So let's prove this just a fact, okay? Let's prove this just a fact. Just a trick. All right, how do you prove this? Prove. Under our assumptions, the function P for product, from the product group to G, which I'm going to define for you right underneath, which takes a pair and sends it to their product. This is always available, folks. This function is always available. I'm not doing anything. But under our assumption, this function is a homomorphism. All right? H1, K1 times H2, K2 gets sent to well, I'm not going to write it out. Just you write it out. You write it out for yourself. Okay? The fact is you can. It's this. Let me write it like this: H1 K1 times H2 K2 equals H1 H2 times K1 K2. There. It's this fact. That translates into this map being a homomorphism. Great. Now this map, its image is of course HK, which is the same set as KH, thanks to commuting. All right, so I'm not going to prove this part. I'll leave that as an exercise. Okay, so the image of P is HK. Okay. The kernel of P is trivial. Why? Okay, if H times K equals identity, then K equals H inverse. And therefore K is in H. But there's only one element that's in both K and H. The identity. Okay, so K equals identity, and so H equals identity as well. In other words, the only pair H comma K that gets sent to the identity is identity comma identity. It's injective. Therefore, the map I replaced G with its image. You can always do that, because that's where the outputs land. This map is an isomorphism. It's a morphism it's a homomorphism that's injective and surjective. Great. Okay, so you can use trick number 3 to figure out the structure of potentially a large chunk of the group G if these two stars align, okay, sometimes you could make number 2 happen. If trick number 2 here worked out numerically, worked out, you analyze this thing and you know what? This conjugation map has to be trivial. Hopefully that works out for you. And sometimes it does. And that's what I mean when, what can you do when you have a normal subgroup? Sometimes these tricks help you do a lot. They get you pretty far. All right? And I'll show you one instance of this week, for sure. How to pull these levers and exploit normality. Just in as far as pure group theoretic arguments go. All right? So, finally, what I should do is, now that I have time, is to maybe talk about some of the tricks that we know so far. Summary of tricks so far. So, in addition to those tricks, Okay, so in addition to those tricks, okay, you all, remember you have the HK trick. This is a counting trick. This is just a counting argument. All right, so you got that one. You have Lagrange's theorem. The order of a subgroup divides the order of a group. So what this leads to is divisibility constraints. Those can be exploited. What else do we have? We have the ability to confidently produce elements of prime order. This is the converse, the partial converse. It has a name. It's called Cauchy's theorem in group theory. One of Cauchy's 10,000 theorems. Okay, so same with Lagrange. Lagrange's theorem. Which one do you mean? Okay, then, okay, what else do we know? Right, conjugation. From G to automorphisms of G is a group homomorphism. Not just a random map. And so the kernel of this has to divide, the size of the kernel has to divide the size of the group, and the size of the image has to divide the size of the image group, etc., etc., etc. Conjugation is not just a random action of the group on itself. It's an action by isomorphisms of the group with itself, by automorphisms. That is a very important observation. Next, using these kinds of actions of a group on itself, like conjugation typically, orbit stabilizer. Applied to these kinds of actions. All right, so the amazing thing is orbit stabilizer stuff. So that includes Bernstein's lemma. Includes Burnside's lemma. In this part. Okay? So look, you have this to play with. You have things like conjugation, or even sometimes the left action on cosets. Conjugation happens to be a really, really good one because it's by group automorphisms that you're acting. So, but you have these basic things in the beginning. You can easily cook up elements of prime order if you want. All of these in conjunction, including the 3 tricks that I introduced, trick 1, trick 2, trick 3, and these kinds of tricks that we had before. All of them in conjunction get you an insane amount of mileage. All right? And we're going to see that as we go. But even this week, you can already prove. You can go ahead and prove now. You have the tools. That any group of order 35 is abelian. In fact, you can say more. You can tell me exactly which group it is up to isomorphism. There's only one. So you can whereas in the beginning, in the first week, I'm probably talking to AI really, or whoever asked that question, that great question in Discord the other day. Like, how the heck does case checking go? Well, imagine if the first week I said, hey, look, group of order 35. Tell me what it is. Well. You got the identity element. Now, pick an element that's not the identity. And let's look at the multiplication table. 35 by 35. Now let's it's insane. But we develop these simple tricks one at a time. And now this particular problem crumbles in like 2 lines. Okay? So it's important to appreciate how the little tricks can be, how much mileage you get out of some of these tricks. It's amazing. And we'll see it this week. All right? So this week, for example, I'll advertise something. Advertisement. Here's a classic theorem. Every group of order p squared, p is a prime, is abelian. And it's either z mod p cross z mod p or z mod p squared. Either one of these two. All right? So this is like every group of order p is of course abelian by Lagrange's theorem. It's z mod pz. But it turns out that every group of order p squared is also abelian, and it's these two possibilities. And we also know that every group of order 2p is either z mod 2p or the dihedral group. So you get these like slow little incremental classification results that chip away at the enormous zoo of all possible groups. We can actually get places by just pulling these levers in the right order. No, you can't make it any group of order p times q. That's in fact, no, you can't do that. Or for example, and there are examples where q is 1 mod p that generalize L. Wombo's example, which is D3. Yeah, there's a whole series of troll examples, kappa. But when p and q obey certain incompatibilities as far as modular arithmetic go, then you can conclude. And you conclude just by using tool number 2. tool number 2 in conjunction with tool number 3. And tool number 8 or whatever. You can get really far in life with these tools. Okay, great. So there was too much abstract strategic lecturing this time, but I wanted to do that on purpose because students were like wondering, okay, so how do we use normality? And so I hope this gives you some insight into how that works. Next class, we will try to find as many normal subgroups of the symmetric groups that we can. And hopefully we'll get stuck in S5 because there's a reason why we get stuck in S5 when you're hunting for normal subgroups. So I want to do something explicit, and I'll do that as the explicit part of next class. Okay. Kappa, you should work this out. You should work it out by considering trick number 2, Kappa. And remember, I told you how to use trick number 2. Typically, the main usage is first, make sure you understand your K. Second, understand your automorphism group of H. And then, hopefully, there's not very many options for this homomorphism. That's how then you'll see what the importance of 5 and 7 are relative to each other. Okay, so you're gonna have to know how to like understand the automorphisms group of, say, a cyclic group of order 7 or order 5. One of those two. Okay, so actually order 7. Okay, great. So let's now stop because I have to prepare my lecture for Calc 2. Hopefully everyone has a good day. Hopefully we had educational experience today. Also, students, please review the logic for why the normal subgroup assumption is so critical in constructing the quotient group, the group of left cosets. You'll see in the literature people just being sloppy, saying, why are normal subgroups important? Because the quotient, the set of cosets becomes a group. And then they don't put the last clause. But you have to understand why that last clause is so important. And you'd really just have to trace through the logic yourself in order to understand that. Like the book also does it in the first line of the chapter. It seems to just be passed from old... it's just a oversight. An important one for beginners that gets passed through the generations. All right. So with that, I will see you all later. I do have to go. It was great to meet you all. You guys are great. Tropical, good to see you. You didn't redeem it, but here you go. 1, 2, 3. There's your thing, Tropical. And I now really have to go. So outro. Here's an outro, folks. So get out of here. Stream is ending. Please leave. Oh yeah, no problem, Tropical Geek. Awesome. Greetings, Zoiku. Now I press. Okay, people are still here. Get out of here. Of course, Kappa. Thanks for coming. You're not even in the class. Thanks for coming. Okay. Thanks for asking good questions. All right. I'm leaving. Okay, you're staying to watch. Yeah. Okay. Well, this is what you get.